Good morning, students. Today we will explain, or today we will see what are the different types of threads that we have available to work with in an operating system. In the last class, we already discussed the concepts of thread. So basically, what we know from our previous knowledge, a thread is basically a type of lightweight process. A thread also maintains, the operating system actually also maintains thread ID, a program counter, a register set, and and the stack to maintain a thread. So basically, the threads belonging to the same process shares its code section, data section, and other operating system resources such as open files and signals and all those things. So basically, a thread can be managed more easily than a process in relation to the working of an operating system. So today we will proceed from that part actually. So basically types of threads. Now as we know, basically there are two different types of threads. One is user level threads and another is kernel level threads. Now coming to the user level threads, basically user level threads are created in the user space, and the operating system kernel does not have any knowledge about the creation of the user level threads. So basically a user level thread implemented in the user level libraries, and the thread switching does not need to call the operating system and to cause an interrupt to the kernel. So basically, the kernel is actually unaware of the user level threads. Now, because the kernel is unaware of the user level threads, all the thread creation and scheduling are done in the user space without the need for kernel intervention. And user level threads, they are generally much faster to create and manage. Now coming to the features of the user level threads, as I told you, user level threads does not require modifications to the operating system, and it is very easy to represent and manage. User level thread can run on any operating system, and user level threads are fast and efficient. As because we are not involving the operating system kernel in the creation of the user level threads, it is generally faster to create, and it's also much efficient. Now, what are the disadvantages? Now, there is a lack of coordination among the operating system kernel and the user level threads, as because the operating system is totally unaware of the creation of the user level threads, and it generally assumes that the process is single threaded, it is not multi-threaded. And ULT, that is user level threads, require non-blocking system calls. That means multi-threaded application, if one of the user level threads makes a blocking system call, it will make the entire process blocked. It means other threads belonging to the same process also cannot run. So that is one of the disadvantage of the user level threads. Now coming to the kernel level threads are generally managed by the operating system kernel itself. That's why it is somewhat more heavier, or it takes somewhat more time to create or to manage the kernel level threads. Now, because the thread management is done by the operating system, kernel threads are somewhat slower to create and manage than the user level threads. So basically, the kernel performs the thread creation, scheduling, and the management of the kernel level threads in the kernel space. And the kernel threads are supported directly by the operating system. Now see here, since the kernel level threads are being managed by the kernel itself, if a thread performs a blocking system call, the kernel can schedule another thread in the application for execution. That means in multiprocessor environment, the kernel can schedule different threads on different processors basically. That means see, one of the threads makes a blocking system call, another threads can be scheduled and can be run by the operating system kernel. So no problem with that. So this way they are different. Now, the features of kernel level thread, I already told you that kernel can simultaneously schedule multiple threads from the same process by the processors. If one thread in the process is blocked, and the kernel can schedule another thread of the same process. That means a particular process consists of several different threads. Uh, if one of the thread makes a blocking system call, another thread can be run. Here, the blocking system call means the particular thread takes the attention of the operating system to implement one of the activities of the particular thread, which it cannot be doing in isolation. And ultimately, the kernel routine themselves can also be multi-threaded. So those are the advantages of kernel level thread. And then to the disadvantages part, kernel level thread are generally slower to create and manage, and kernel requires a thread control block or TCB for each thread in the pool, hence complexity increases. As you have heard that a process has been maintained by the process control block by the operating system, in the same way thread control block is also being implemented in case of kernel level threads, and definitely it will be somewhat, it will increase the complexity somewhat, so the management of the thread can be made easier for the kernel. So those are the features of kernel level thread. Now basically there are three different threading models which we can implement. Those three threading models, they're termed as many to one model, or one-to-one model, and many-to-many model. So basically, the operating system provides a combined. So some operating systems basically provides a combined user level and kernel level thread facility. As one of the very good examples of this is Solaris. Now, at the very beginning, we have the many-to-one model. So basically, in case of many-to-one model, the model maps many user level threads to one kernel thread. The thread management is being done in the user space, so it is efficient, but the entire process will block if a thread makes a blocking system call. Also, because only one thread can access the kernel at a time, multiple threads are unable to run in parallel on multiprocessors. So basically, only one thread can be accessing the kernel. The other threads cannot access it. That is a feature of many to one model. So it is not very much efficient, we can say. It is somewhat efficient. Coming to the next model, that is the one-to-one model. The main feature is that for every user thread, you are having a corresponding kernel thread also. That means it maps each user thread to a corresponding kernel thread. It provides more concurrency than one-to-one model by allowing another thread to run. Another thread makes a blocking system. It also allows the multiple threads to run in parallel on multi-processors. Now, what is the disadvantage here? The only drawback is that creating a user thread requires creating corresponding kernel thread also. And the overhead of creating the kernel thread can burden the performance of the application. So basically, most implementations of this model, what they do, they restrict the number of threads supported by the system. That means they cannot go on creating user threads at a very large level. That because the corresponding kernel thread also needs to be created, and that will burden the performance of the system. That will burden the system actually for maintaining the optimal performance. So there is some sort of limitation that we have to impose here in case of creating one-to-one models. And lastly, we have the many-to-many model. So the many-to-many model, what it does, it creates many user level threads to many kernel level threads. It avoids the limitations of the one-to-one model while extending the multi-threading capabilities even further. So basically, the many-to-many model multiplexes many user level threads to a smaller or an equal number of kernel threads. We don't have to make equal number of user threads and kernel threads at this particular implementation. The number can vary, but basically uh, we are creating several user threads and several kernel threads also in this model. Now the number of kernel threads may be specific to a particular application or a particular machine also. Now developers can create as many user threads as necessary, and the corresponding kernel threads, they can be run in parallel on a multi-processor architecture. So basically, when a particular thread performs a blocking system call, the kernel can schedule another thread for execution. So these are the various thread models that we can implement in relation to a thread architecture. So that's all for today. Thank you.